Today, I'm specifically going to focus on vehicle detection in drone imagery. So just basically detecting vehicles in aerial images. Just a bit about myself. I'm currently pursuing my master's in computer science at Western University. My research interests are in anomaly detection, deep learning, and computer vision. I also have some practical experience in the last year or so, working as a computer vision engineer at Mitacs, where we're partnered with industry partner SkyDeploy, working with drone data. And I've also held positions at Vector Institute, Spot App, and a few other places. So specifically, what we're going to be discussing today is vehicle detection. So we're looking to build a system that, given an input image, which is an aerial image of a scene, maybe captured by a drone, maybe captured by a satellite, we're looking to identify the vehicles. So more specifically for each vehicle, in this image, we're looking to predict a bounding box, which is basically going to give us the XY location of where the vehicle is, as well as its height and width, as well as a categorical label. So in the most simple case, we can have vehicle or no vehicle, but we can also do multi-class classification, where we can classify a vehicle as car, truck, or no vehicle, etc. So this is the basic formulation of what we're trying to do today. So just as a brief agenda, I'm going to go through a quick introduction on object detection, focusing on deep learning based approaches, then go through a specific RCNN object detection approaches at a very high level, and then get into vehicle detection and aerial imagery. And I'll try to end off with some kind of more practical tips that maybe people can get some use out of, besides the theory I'm going to go over. So as an introduction, maybe more broadly to computer vision is an area of research where we take a look at images, videos, etc., and try to perform tasks on them. So three very simple but popular tasks in computer vision are: given an image, we want to classify what's in the image. So that would be classification. And then object detection, which is kind of the focus of this presentation, is basically for each object in an image, we're looking to output a bounding box, which gives us the size and the location, and also a class label. So in this instance, it would be cat, and this would be a dog. And then there's other tasks like semantic segmentation, where for each pixel in this image, we're looking to output a class label. So everything else would be kind of background, but these pixels would be classified as cat and dog, respectively. So like I said, I'm going to be focusing on deep learning for computer vision. So hopefully you've encountered at least deep learning in some sense before, but I'll try to keep it as high level as possible and not get bogged down in the technical details. But all in all, deep learning has enabled near human level performance in the aforementioned tasks. So kind of the secret sauce, or what's been kind of the reason we're getting all these really impressive results, is we're employing convolutional neural networks that are basically iteratively applying these learned filters to the image and subsequent features to build rich representations of image that are used to accomplish a downstream task like image classification or semantic segmentation. So there's minor differences in the architectures, or how these systems are designed per task, but kind of the core principles remain the same. So just to be more specific, we could see this is AlexNet, an architecture for image classification, and you could see here we have depicted convolutional layers that were iteratively kind of refining these features, all the way until we have basically a vector or a list of 1,000 numbers that represent the 1,000 classes we're trying to classify over. But the gist is of the whole process is we're going from an input image all the way to these predictions by way of these convolutional layers. In the case of semantic segmentation, it's very similar. You could see the first half kind of here, it looks very similar to what we have in AlexNet. But since it's used to do semantic segmentation and not image classification, we basically also have the addition of this decoder, which basically upsamples the features back to the size of the original image, so that we can basically say for each pixel, what's its class. So what I'm trying to get across here is basically the architectures or design of these systems may vary a bit across tasks, but kind of the core principles, which is just convolutional neural networks, kind of remains the same between different approaches. But we're going to be focusing on object detection today. So we're looking to basically, for each object, predict a bounding box and class label. Object detection and vehicle detection could kind of be used interchangeably. Vehicle detection is just an instance of object detection. So we're going to start with just a brief intro to object detection, see a few of the more recent approaches, and then get into specific instances of vehicle detections a little bit later. But the formulation of the problem is the same. We're basically, for each object in a scene, we're looking to output a bounding box. Like in this case, it's a car and a category label. So the label is car, and then we have the bounding box kind of highlighting where it is. And the same goes for other objects in the scene. So you may ask, how do we evaluate the performance of an object detection system? So you could think we have kind of ground truth labels of bounding boxes where objects actually occur. So we can see that depicted in the green box here. And our object detection system is basically going to predict a bounding box. And to see how good kind of this prediction is, we could use the intersection over union, which is basically looking at the area of overlap between the ground truth box, which we know is the true object, and our prediction. And then we divide it by the area of the union. So this is between 0 and 1. And we could define something like maybe 0.8 to be kind of our threshold to see if this is basically an accurate bounding box, that this is actually covering an object. So with each of these kind of predictions, we can aggregate using kind of mean average precision, which is ultimately what object detection systems report if you read any of the academic papers. And that's basically looking for each prediction and each ground truth bounding box. We're going to take them into account and calculate a precision and recall curve, which you can see depicted here, which I'm sure a lot of you are familiar with. And basically, we want the area under this precision recall curve to be as close to 1 as possible. So it basically means the higher it is, the better our object detection system is performing. So to get into some challenges in object detection, one of the main challenges is that we're looking to predict multiple objects per image. So it could be a variable amount of objects in each image. And these objects could have different shapes, sizes, and classes. The second challenge is occlusion. So objects may be occluded by other objects or by the field of view of the camera. Third challenge, multiple outputs. So we're trying to build a system that's not only going to output a label for an object, but also a bounding box that shows where and how big it is. And then the fourth challenge in these object detection data sets or in the real world, we generally have high resolution images in complex scenes. So this means a high computational cost, and it makes it a little bit more of a difficult task. So I'm going to quickly outline some RCNN object detection approaches. I won't get in too deep to the details because I don't want the talk to be too dense. And hopefully some people have some prior experience with this that kind of helps them kind of understand certain elements. But the first RCNN-based approach is depicted on this slide, and I'll start by explaining kind of this pictorial down here. So we have an input image that we're looking to basically do object detection. We could maybe say we're looking to detect humans and horses. So the first step of the process is basically to extract region proposals, and region proposals are just kind of initial bounding boxes of where like objects may occur. So it doesn't have to be 100%, but there may be an object occurring within this box. So we can extract a number of these region proposals. In RCNN, they extract 2,000 proposals per image. And for each of these proposals, they're going to resize it to a constant size and feed it into a convolutional neural network, similar to the architectures that we saw earlier, which we're going to get a feature representation of the image. And with those features, we're going to basically both predict its class of the region proposal and a bounding box that kind of refines our estimate of where this object occurs. So if we look on the right-hand side, we can have a region proposal that's generated by this selective search algorithm. You could search it up if you're interested in learning the intricacies of it. But basically, we're going to generate a bunch of these proposals that we resize to fit in a convolutional neural net. We get the features, and then we can use an SVM to do classification. And then we have a second head, which we do bounding box regression, which is going to basically refine the prediction we have about the whereabouts and the size of the object. So the pros of this approach is that we're able to actually do like predict the location and size of multiple objects along with their class label. And we have this region proposal algorithm that helps us to kind of narrow the search space of where objects can occur and give us a good starting point. But the cons are, for each of these region proposals, we have to feed it to the convolutional neural net. And if we're generating 2,000 proposals per image, like this is very computationally intensive. So both training and testing take extremely long, and real-time systems weren't really practical with RCNN. So in response to RCNN, this paper, Fast RCNN, came out, and it basically had a very similar structure, but instead of having a separate forward pass of the convolutional neural network per region proposal, we're going to generate the region proposals in the same manner we did before, but we're just going to project them onto the convolutional features. So basically just overlay the region proposals onto the convolutional features. But since these features are usually a fraction of the spatial resolution of the original image, we kind of have to scale the aspect ratio of them. But basically, for each region proposal that's been projected onto the features, we can use what's called ROI pooling to get a feature representation of that specific region proposal. And then we feed it to basically a two-headed network like we did before, that one side is going to predict the class of basically the region proposal, and the other one is going to refine kind of its size and location so that it's more accurate, because the region proposal network is just going to give us very rough region proposals. So the pros of this is that we're sharing the convolutional features and computation across region proposals. So instead of having to do feed the convolutional neural network like 2,000 region proposals, we feed it the entire image once, and this results in significantly faster training and testing time. But the cons are the selective search algorithm that we're using is basically the bottleneck time-wise. And it kind of is external to our system, so we can't really learn the mapping end to end and reap the benefits that come from that. So in response to kind of these drawbacks, faster RCNN was introduced, and it's basically the same exact idea, but instead of using selective search to generate the region proposals, we're going to use another convolutional neural network with a very similar architecture. And we're going to share kind of these features across the two components of the network. So you could think of this region proposal network is basically subbing in for the selective search algorithm. So this is one component that is going to generate our region proposals. And then those region proposals are yet again projected onto the features that are generated by feeding the entire image to the convolutional neural network. Then we do the same ROI pooling to get representations of each of the region proposals, and we do the classification and refine the bounding box just like previously. So the pros are basically we're learning the mapping instead of using this selective search algorithm, and it's also a lot computationally faster. So if we take a look at this quick summary slide, we can see that the three kind of approaches we went over, RCNN, fast RCNN, and faster RCNN, are ranked in terms of how long it takes to run, and basically the mean average precision, which is the metric of success that we kind of briefly discussed earlier. So in the first approach, it takes 50 seconds just for one image, and in faster RCNN, it only takes 0.2 seconds. So this kind of enables a lot of real-time applications. Still not fast enough in some circumstances, but definitely good enough for some scenarios. So to quickly discuss some vehicle detection and aerial imagery approaches that extend the previous object detection approaches we just discussed, I'm going to go over two papers. So reminder for vehicle detection, we're basically doing object detection, but specifically looking at vehicles, looking to output for each vehicle instance the bounding box and the category label. Like I said, vehicle detection is just a specific instance of object detections. However, popular object detection models don't work well out of the box for vehicle detection. And this follows from like the differences that aerial imagery have from regular images. So typically when we have a drone or satellite imagery, the objects in the image may be kind of very small. And this is the case, especially in vehicle detection, where the objects instances are very are much smaller than other applications that are kind of used in the literature to kind of develop and test these approaches. So there's been some recent works that have explored kind of fine-tuning these methods and coming out with different methods to extend and adapt the current methods to have better performance. So one of the papers is this comprehensive analysis of deep learning based vehicle detection in aerial images. And they basically extend fast RCNN and faster RCNN to work within the context of vehicle detection in aerial imagery, specifically for drones. So they perform an analysis on different region proposal methods to see what performs the best, and they identify performance optimizations and assess their performance. But the main motivation is basically adapt fast RCNN and faster RCNN to handle smaller object instances. So it's basically, this is the architecture that we're working with. We're just going to fine tune it a bit specifically for the context of vehicle detection. So the first thing to do is in the region proposal network, we have what are called anchor boxes, which kind of are applied at each activation in the feature map. And they're basically act as initial prediction of where an object may occur. So basically, the faster RCNN method is optimized for larger object instances, like I said. So basically, these anchor boxes are going to be way too big for the vehicle instances. So the first very simple optimization is just to change a hyperparameter in the network that defines the size of these object instances. So basically, in essence, what we're trying to do is make sure that the anchor boxes are closer to the size of the actual objects that we're trying to predict. The second optimization along the same vein is to increase the feature map resolution. So like I said, we use like these convolutional neural networks to process an image and get its feature representation. And that feature representation is usually has a lower spatial resolution, but more channels. So we kind of lose some of the spatial information by downsampling it like that. And when we're dealing with small object instances, we want a higher resolution. So the second optimization that worked really well is just to use earlier layers in the convolutional neural network that have a higher spatial resolution. So that was the first paper. Going quickly on to the second paper, another challenging task in vehicle detection is that most object detection methods don't consider the orientation of the bounding boxes. So when we're predicting the bounding box for a vehicle, it's not going to have an orientation associated with it, which is important in a lot of applications. So this paper, which is called R3net or R3net, is basically, its main motivation is to detect vehicles of different orientations. So it's the architecture looks pretty scary, and I won't get into it too much, but it's very similar to faster RCNN. And in that, there's kind of two components. There's a region proposal network that is going to generate kind of our initial guesses of where objects may occur in the image. And then we have the detection network that is basically going to refine these initial proposals and predict where the actual objects are in their classes. So basically the paper uses same kind of architecture, but they also want to bake in the fact that we have to predict the orientation of vehicles in terms of just kind of a yaw angle, you could say. So this is the architecture, and like I said, I won't get too bogged down into the details, but like you could see, there's two core components: the region proposal network, and you can see there's an R, which just means it's a rotatable region proposal network. So it functions to do the same thing as the region proposal network in faster RCNN, but it also can predict orientation of bounding boxes. And then the region detection network is the same exact as fast RCNN. We're taking the region proposals and this additional orientation information and trying to refine those predictions. So I'll get into 3 tips that kind of are very helpful in practical scenarios, because I know this has been pretty theory heavy. So the tip 1 is to leverage existing data sets. So if you're looking to do vehicle detection in aerial imagery, you don't have to go out and capture an entire data set with thousands of images, which can be quite expensive and time consuming. So there's publicly available data sets that have aerial images in them, and they also have annotations in the form of bounding boxes and the corresponding class. So you have everything you need to basically train a vehicle detection system from these publicly available data sets. So for some applications, maybe you do have some existing data. It's still useful to kind of use these data sets if they're relevant to your data set to kind of pre-train or have more data to train on to increase the performance of your system. Another one is a lot of these drones, depending on what drone you're working with, but even as simple as consumer drones like by DJI, you're going to get a lot of metadata that you can use to enhance your vehicle detection as well as achieve related tasks. So some of the metadata that is included is things like drone height, GPS location, the drone yaw pitch roll, the drone's camera, yaw pitch roll, camera focal length, sensor dimensions, all this stuff and more. So it's very helpful in some cases. So one specific instance that I've kind of leveraged this is basically using, we could take the altitude, the camera focal length, and sensor dimensions and get a rough estimate of the ground sampling distance of our images, so that we can better initialize the size of anchor boxes for object detection models. So that's definitely something you might want to look into. And also just pose related information of the drone is helpful. If you're capturing multiple images of the same scene, you can use that to kind of reconstruct the scene in terms of a 3D reconstruction if you have ground control points and other associated information, or just make a mosaic, like stitch the images together. Both of these are kind of relevant to doing vehicle detections across like a wider scene than just can be captured by a single image. And there's also a lot of like really great software. I think there's Open Drone. I don't know if that's a specific name, but if you look around, there's some kind of services that kind of do this 3D reconstruction or image stitching for free. So if you're not looking to build that out by yourself, definitely look into services like that. And then last tip is to leverage data augmentation. So like I said, to capture like aerial imagery is sometimes very costly, especially if you need a lot of it and different scenarios. So one thing you could do to make your vehicle detection more robust right out of the box is just to apply perspective transformations to images in your image set, and obviously apply the same perspective transformations to the annotations. And then you could kind of get more data from different perspectives, and this will help you have a more robust system.
In general, which is faster to achieve, semantic segmentation or instance segmentation?
What is faster to achieve? So I guess in instance segmentation, I'd say that's a bit harder of a task, just because we have to, well, semantic segmentation is, like I said, for each pixel in the class, we're trying to output its class. But in instance segmentation, if there's two dogs in an image, we have to like identify each of the instances. So I don't know if they're getting at the computational complexity. I think maybe it would be relatively consistent, but I think instance segmentation is definitely more complex to perform, but definitely two very related tasks. So good question.
Have you considered using other CNN networks, ResNet, or Vision Transformers, Convit? And if yes, what's making you stick to AlexNet?
Well, just for this talk, like this isn't kind of presenting or endorsing any sort of approach. I just kind of wanted to build it up from kind of some of the first object detection approaches, just because I didn't want to get too technical and lose some people. So I wouldn't say that's specifically what we're using, and that's definitely a great point. So when we're getting these features that we're using to do the downstream tasks, there's been a lot of innovation since AlexNet. So there's ResNet, which is super popular, and that's actually what RCubeNet uses. And I didn't mention that, so sorry about that. But it's definitely, you want to get the best features you can to get the job done. Yeah, just I was kind of trying to stay true to the papers I was presenting, like faster RCNN and stuff does use AlexNet or VGGNet. So I was just presenting those architectures.
In your field of work, do you detect new object class or classes using transfer learning of AlexNet?
So it's definitely a topic that's popular in the literature. I don't know if they're getting at kind of out of class detection, because there's been some really cool recent work in basically trying to predict something that's never been seen by the network before. And in the simplest case, it could be something like anomaly segmentation. So what I was showing you is semantic segmentation. We're trying to classify each pixel into its class, like cat, dog, or background. But for we could make that more robust, because in certain times we see things we don't expect, like in it's popular in the self-driving data sets. Like if there's an object on the road that's we haven't saw yet, we still want to be able to detect it. So we could do anomaly segmentation, and that's definitely something that's kind of like out of class detection. And there's also more research in that kind of area. So I encourage people to kind of look for that, because it definitely is out there.
Do you face challenges of less or one sample of data with respect to a class? If yes, what's your approach to handle it?
So in this specific case, I'd say in the context of vehicle detection, like for some tasks, like it can just be like binary classification, like is there a vehicle or is there not a vehicle? Because for a lot of applications, like maybe you're trying to get a heat map of a parking lot or something with each of the stalls. You're just basically looking to see if anyone's parked in there or not. And then if you want to extend it to like maybe be able to discern between cars and trucks, if that's relevant to your application, that's also pretty standard. So I'd say in vehicle detection, the classes are usually pretty well defined. But in other applications, like I said, self-driving, if we're looking to segment objects that we've never saw before, it's very important to do so. And there's kind of, like I said, research in that direction that you can definitely check out. That's pretty recent.
The paper you mentioned on aerial vehicle detection seems to be using the faster RCNN family. Would be curious to know how YOLO SDD would do.
So yeah, like I said in the presentation, there is kind of different classes of object detectors. One of the classes is kind of these regional convolutional neural network approaches, or they're also referred to as two-stage detectors, because we first generate the proposals and then we kind of refine those proposals. And then there's another class of object detectors called one-stage detectors, and we basically go straight from the image to the predictions. We don't have to kind of have the first step of generating the proposals. Basically, both of these get pretty similar performance, especially in the most kind of recent iterations of one-stage and two-stage detectors. But one-stage detectors definitely have some benefits in terms of the computational costs. Like you don't have to do the proposals first. So I think in terms of computationally complexity, at least, one-stage detectors like YOLO are good for some applications, like real-time systems.